vector calculus that account for the velocity component perpendicular to the area. And the cases that I want to examine, the three cases, will be theta equal to 0, theta equal to pi over 2, and theta equal to pi. And I want you to tell me what is the cosine of 0. 1. And hence is rho VA, and that corresponds to the alpha. What happens if theta is 90 degrees? Velocity is perpendicular to my surface area. What's cosine 90? 0. Nothing going in. If the velocity of this breeze of wind is parallel to my garage door, nothing goes in, and it's 0. What if it's negative, or what if it's 180 degrees? What is cosine 180? Negative. Minus rho VA, and that represents the in mass flow rate. It's a little lengthy, and it's a little maybe too detailed, but I thought taking time to go through that let you appreciate how I may now modify this equation one more step. So that I can lump both of those in and out mass flow rate together by simply taking advantage of this so-called dot plot. This is now a little closer to the final form that I wanted, and that will be very critical in dealing with the momentum equation. All this time is spent on this continuity equation to set the stage for what we need for the momentum. So I know this may be tedious and trivial, but trust me, when we go to momentum, if you don't understand this, you have no hope of understanding momentum. The sign, the nomenclature, the convention, etc., etc. Yes?
The in and out. Okay, I think I got this. But the you have like the positive up there and the negative in there. That becomes the in and the out. And that's why you combine those terms.
You got it. Yeah. Not all of you can get this. Go home, sit down, and think about it. Look at this dot product and go through what I did, and you will find that it's all now completely represented by one term and one term only. This represents both in and out. The plus and minus sign will take care of itself. Got it? Okay, so I'll give you a 2 minutes break. When we come back, we'll start looking at momentum equation. Okay.
students ask for
That's weird that all the causes are
So let's pick it up again. The remaining class will be mostly focused on the first application of the momentum equation. And I cannot emphasize the difficulty and the challenge associated with the momentum equation, where sign and the physics can be very daunting. So I'm going to strip it down to the bare bone, just like I did with the continuity with the water tank problem. I'm going to approach it from, say, a very simple problem, where I have a circular jet. This is like a riot in a city that the police shoot a water cannon towards the crowd, and I want to know if I shoot a water cannon towards the plate, what force I have to apply here with that plate to the effect of water jet. Right? Make sense to you? So give me some idea of what kind of perimeters may influence the force that I have to anchor to hold the plate stationary. Any idea about what will affect that force?
pressure.
Pressure, okay. Yeah. What else? Pressure actually translates to the velocity, right, which we will see how that relate later on by Bernoulli. So I will, instead of pressure, I call it U1. What else? Yeah.
The shape of the plate.
The shape of the plate turned out to be inconsequential. Because as long as I deflect that and it's back radially, that's all it matters.
The amount of mass that you're throwing.
The amount of mass will be, maybe I would change it to, yeah?
Distance from the plate.
Distance from the plate, again, it turns out to be inconsequential. Those are all good questions. But I can see why you're asking that. I mean, if in the real life, so we're idealizing this situation. The jet doesn't deflect, the water doesn't splashes, you know. So whether I'm 1 foot from the jet or 10 feet, the jet behaves the same. It's not spreading. It just continues this same shape until it hits the plate. So very idealized, simplified situation. Yes?
The area of the nozzle.
The area of the nozzle. Very good. Area of the nozzle. So I call it diameter. How big is that jet? An inch versus a tenth of an inch versus 1 foot. You can see it make a big difference upon hitting the plate. What else? Yes?
Density.
Density. If it's an air cannon versus a water cannon versus an oil cannon, that first order effect. So I also care about the density. So what is being asked is that find me the force as a function of, which is what we just lay out, type of fluid, water, and I know the density, how fast the jet is hitting me, which is a function of the pressure, how big. So this geometry, like the lubricating oil problem, is what we call axis symmetric, and it's otherwise not two-dimensional. So the jet, because of that, will spread. Let me try to put it here. The lubricating oil problem. The jet in the center of the plate, and it will spread radially. And some other assumption to make the problem more trackable, steady. No body force, meaning gravity is not important. The water jet is not going to be influenced by the weight of the water. Or no gravity. We're going to also flow in a neutron. If you haven't seen that before, we'll explain it. Inviscid. Anyone want to know what that means? Inviscid. Anyone else? You remember? Inviscid? Yeah.
It's like assuming no viscosity in the.
No fiction? Yeah, no fiction. And the fact that ambient atmospheric pressure, which I call PA, is everywhere, including in the jet. And the jet deflect is not, it's a circular stream and then it's spread radially into a cylindrical disk. The pressure, 14.7 or 100 kilopascals everywhere within this jet and the space. All right, do you picture the problem? Yes?
So, this might be totally off, but if you were to like increase the atmospheric pressure, like do this like a chamber, does that mean that it would provide more force?
If, as long as the pressure everywhere is the same, if you do this in a 2-atmosphere chamber, they still all cancel out. Right? And we will come to that later on, and I think that will become very apparent. But for most everyday application, you deal with ambient 14.7. So what's the first step in analyzing this problem? Control volume. Very good. Get that habit. You have to draw a control volume before you tell me what you're analyzing. So this may or may not be obvious, and drawing a control volume is not a trivial decision, but with example and homework, it will become more and more apparent. So we're going to choose a control volume as shown, and I have 2 stations then. One is axisymmetric, cylindrical water jet. 2 as the exit. Both top and bottom are on this circumferential wing. And then we're going to also establish a coordinate system so that we can know what is plus and what is minus sign. Very important. So I'm going to choose x positive to the right, parallel to the positive velocity of the jet. Y is vertical, positive. So that is the reference coordinate we will use for all the signs that follow. Okay, any question on the problem statement? So before we dive in, let me take a moment to divert just so that I don't forget at the end of the class. This is the last homework problem, very simple. It's analyzing wire continuity, the jet engine of the Portway of Atrium here. You are told the flow coming in at the inlet of the engine, density of air being pulled in, fuel is added, density is given, and the mixed combustion product come out and stationed at the exhaust. There's only one hint that I want to alert you to. What assumption you cannot make on this problem?
Density is equal.
Density is equal. Right? It's not equal. It's combustion. The air expands tremendously. The fuel is added, temperature is much higher. So density is not equal. Once you see that, problem is piece of cake. Okay, so back to momentum. Let me do a revisit of the system equation for momentum. Right? F equal to ma. You've seen that before? I added now a subscript x because I have more than one direction. and X and Y. So this applies to the X direction. And there could be a parallel one, which we won't deal with for this particular problem, in the Y direction. Now this is the most convenient form you have seen and used, but it actually can be altered into something more appropriate for fluid. Is this the same? Is it? Yes or no? The answer is yes. This is called the rate of change of X, and I use the word linear momentum. So it wasn't mass times acceleration. If you're more specific, what Newton said is force changes the linear momentum. Right? But it's just for many of our applications, it's just as easy to look at it as mass times acceleration, but not in fluid. So what it translates to, if I look at this new formulation of momentum change resulting in a force, this is actually equivalent to m dot times the velocity in the x direction. That is what we will use to analyze fluid. If you toss me a baseball, just like that water cannon, at me, and I want to hit it with a bat and change the momentum, that's the equation I use to calculate the force. I need to change the momentum of that baseball. For fluid, this is more of what I like to use. Same physics, different formulation. And sometimes we, instead of using the subscript v sub x, which is the velocity in the x direction, like I said before, same thing, we use the small u as our nomenclature. All right? Yes?
That's assuming that the velocity is constant.
Yes, it is. Very important. Yes, when we say steady, then the velocity has to be not changing in time. But it doesn't mean it's not accelerating for the reason I've shown here. All right? So that's a distinction between fluid and particle dynamics. Velocity is not changing in time. I have a steady stream of water hitting at me at 100 feet per second, for example. Other questions relating to what you've seen before for a system? So the song and dance meaning the algebra needed to go from a system equation to a control volume formulation is by way of something called the Reynolds transport field, which we'll deal with maybe in another 3 lectures. And the dot 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 allow a transformation algebra that take the system of Edgar MA equation and make it a control volume formulation of momentum that looks summation forces So what I've changed from system to control volume is the forces become now a summation of forces, and I'll elaborate on that more. And that net force acting on my control volume will result in a momentum change. But that momentum change is no longer as simple as mass times acceleration, because that's only applicable to particle. Now with fluid, that momentum change is represented by m dot u, which is still a momentum, for the reason I've shown, out, leaving my control volume, versus or minus that coming in. That is the simplest form for my momentum equation that we will use for many, many applications. And let's see how we use this to solve this problem. All right? So this is our most important equation moving forward. Questions? The force summation is very important to elaborate and examine all the possible constituents. So let me break up the forces here and discuss that further. We call this the net force, meaning I have to account for different contributions, and whatever left, some are plus, some are minus, is what appear on the left-hand side of this equation. So there's a driving potential, which used to change the momentum. That consists of three components, and this is a good example to illustrate what they are. I have the surface forces, meaning forces acting on the surface. I have body force, which is due to gravity, which in this problem we neglect. And finally, I have external, or sometimes in the text refers to anchoring forces acting on the control wall. In this case, that's the anchoring force we are asked to calculate the force F. So we have 1, 2, and 3. Surface forces, what I mean by surface forces, and there are two components of that. Which two? Can someone help me? Viscosity, yeah. Friction. Very good, because it acts on the surface, right? Surface forces. What else? Huh? Normal, what do you mean by normal? I need forces acting on the surface. Normal to the surface, that's correct, but where does that come from? That's correct, yeah. Forces that act normal to the surface. But what forces actually act normal to the surface?
The weight.
Not the weight. Weight is the body. This is the weight.
Reaction?
Not reaction. I'll give you the answer. Pressure.